Well, hello guys, Mr. G here with another video. This time we're going to be doing a question paper for the grade 11th. This one was done in term 1 at the Northern Cape province at one of the districts there, but we are going to be working there. This question is very important because it is going to be in June examination for the grade 11 and 12, the same topics. So we're going to start, but before that, please subscribe for the channel so you can get the notification, the worksheet, and all the videos I post on regular basis. So we're going to start with question 1, which as usual is a multiple choice. A force of 30 newtons acts on an object at an angle of 34 degrees with the surface as shown in the diagram below. The component of the force parallel to the surface, they're looking for the parallel component of the force. Remember, this force can be broken into components, which can be the horizontal component or parallel to the surface or component in the x-axis, which is this one here. If you project this one to the x, let's fix this one here, the length, there it will be the applied force of the force in x, and here in the y-axis will be the force in the y direction. All right, so in this case they're asking you for the horizontal component or parallel component. In other words, is the x component of the force. If you see from the angle we have, this one is going to be the adjacent side, so in this case will be equal to the force, which is 30 newton multiplied by the cosine of theta, which is 34 degrees. The direction in this case will be to the right, and this is the first question. So the answer for this one will be, in the correct one will be a B. 30 newtons cos 34 degrees to the right, and that one is the first question, question 1.1. Let's go to question 1.2. A learner pulls a book at constant speed over a rough horizontal surface with a force F. The force diagram below show all the forces acting on the block. Okay, which one of the following relationship between the magnitudes of the force F, X, Y, and Z is true? Now, important concept here, this is moving at constant speed. Now, in this case, if it's moving at constant speed, according to Newton's first law, if it's moving at constant velocity, then the forces are going to be at equilibrium. In other words, the net force is going to be equal to 0. If the net force is equal to 0, it means the forces that is going to the right must be equal to the forces on the left, and the forces on top must be equal to the forces at the bottom. In other words, if this is 0, we have to know that F must be equal to Y, and we have to know that X must be equal to Z, and that is the case here. So the correct answer will be D, because the forces are at equilibrium. Let's go to question 1.3. Which one of the following statement is true? In all cases, the normal force has the same magnitude as the weight of the object. That is not correct, because it's not always like that. The normal force and the gravitational force form a Newton three action reaction pair. That is not correct. That it could be tricky and people attempt to get confused. For an action reaction pair, the forces must act on different objects. Okay, now the normal force is perpendicular to the contact area. The normal force is always perpendicular to the contact surface. It's always like that. The normal force is dependent on the frictional force. It's not right. So the correct answer is going to be question C, or option C. 1.4. A sphere is attached to a string which is suspended from a fixed horizontal bar as shown in the sketch below. The reaction force to the gravitational force exerted by the earth on the sphere is. Now, the gravitational force on the sphere will be this force here. This is the force of gravity, or in other words, can be also called weight, or even if you want, you can say force from the earth on the sphere. That is what they give you here, right? That is no. Now, which one is the reaction to that force? And let's have a small drawing here. We said that this force here is the force from which with the earth exert on the sphere. This is called weight. Which one is the reaction to that force? Well, this sphere, according to Newton's law of universal gravitation as well as Newton's third law, must be pulling the Earth up with a force that is going to be in this direction, guys. This one is the force from the sphere on the Earth, and this is the reaction force to the force which the Earth is pulling the sphere. So the correct answer in this question will be the force of the bear on the sphere, no. Well, the force of the string on the sphere, no. The force of the sphere on the Earth, that one is the correct answer. The force with which the sphere exerts on the Earth, that is the correct answer for this question. It could be tricky. Question 1.5. There is a question paper done in which it was done for grade 12, but it's very applicable for the grade 11, in which we solve questions like this one. So I'm going to leave the link so you can go there and practice those questions. Two charged spheres are placed x meter apart. The electrostatic force between the two spheres is F. So when the distance is x, the electrostatic force is going to be F. Remember, this F we are talking about is equal to K Q1 Q2 divided by distance squared, but the distance is going to be x, so it's going to be x squared. No, the distance is going to be x there. They're telling you that one in here. Now it's going to be a new situation when they are going to decrease the distance by half, as you have in this side here. Guys, what we're going to do, we're going to substitute. Everything stays the same. The only thing that it was changed was the distance between the sphere, which is now half the distance x. Everything square according to the formula. When you solve this one, you have that the force is equal to K product of Q1 Q2 divided by 1/4 of x squared. And then when you solve this one, you have to multiply by the inverse. So it's equal to K Q1 Q2 divided by x squared multiplied by 4. In other words, if we solve this one, we have in that F is equal to 4 multiplied by K Q1 Q2 divided by x squared. And if you notice, this one here is F, as you can have it there on top. So in this case it's 4 times F, 4 times F, which it will be answer. The correct answer will be A. I hope this is clear. As I said, there is another video for this one. And thus, guys, is question number 1 with a multiple choice. I hope you understand multiple choice are always very important because it's a lot of marks. So let's go to question 2. Two fishermen are pulling the boat to shore. Fisherman 1 pulled it in an easterly direction with a force of 500 Newton. That is F1. So F1, we're going to write it quickly here, is equal to 500 Newton. And fisherman 2 pulls in a northerly direction with a force of 600 Newton. So F2 is going to be equal to 600 Newton. Those are the forces. The first one is going to be to the east. The second one is going to be to the north. This one is the direction that they are giving us there, in which direction were those two persons pulling the boat. The first one is define resultant. Now, what is resultant? Resultant is the sum of two or more vectors. That is a definition of resultant. Draw a level vector diagram to show how to obtain the result to the resultant of the two forces. So we have to add graphically these two vectors, and they are giving us a scale which we have to use. We cannot change that scale, guys. Now, the scale is very easy. 1 centimeter is to 100 Newton. So for F1, we have 5 centimeters. I'm going to write it here. And for F2, we have 6 centimeters. This is very, very simple. Now, to answer this question, you need to use a ruler. I don't have a ruler here, so I'm going to show you the drawing, how it can be done, but without the ruler. You do have to use a ruler. So you have 6 centimeters to draw in the north direction, and this is F2. This is F2. 2 pointing north, remember this one must be 6 centimeters. It must be 6 centimeters north, pointing in that direction. And the other one is 5 centimeters to the east, which will be this one here. So this one is the first one, which is equal to 500 Newton, and you have to draw it with 5 centimeters. That is important. Now, how to add these vectors? Guys, we have two options to draw these vectors. It could be used the tail to head, or can be used the tail to tail. I am going to do it here with the tail to tail method. Now, to do this one, you need to draw parallel line to each of those lines there. So parallel lines, as accurate as you can, it must be done with a ruler. Parallel line, so you can then join and get the resultant. So the resultant is going to be from the two tails of the vectors to the point when those two parallel lines cross each other. So this one here will be the resultant of the two forces. That drawing there will be the resultant of the two forces. So if you have to calculate it graphically, this is one of the options to the drawing. The magnitude will be get by measuring with a ruler from the tail to the head of this vector. And the direction, which is an important point here, could be when you measure with a protractor this angle here. This angle could give you the direction of this specific adding of vectors graphically. That was question 2.2. Now question 2.3 say calculate the resultant force. Now we have to do it algebraically. So we are going to do question 2.3 here. And if you look carefully, this F2 in actual fact can be moved on this side, and that will be what we call tail to head. And if we do that, which is what we are going to do here, just for you to understand what I'm doing, this one here is a triangle right angle in which the resultant force become the hypotenuse. This one is the hypotenuse, this one is the opposite side, and this one is the adjacent side to that angle I have there. So using Pythagoras here, we can calculate the hypotenuse, which will be the resultant force, and resultant force square will be equal to one side square, which is in this case F1 square plus F2 square. All right, so if we substitute this one, we have that the resultant force square is going to be equal to the numbers we have is F1 is 500 square plus 600 square. Fr will be equal to the square root of those numbers there, 500 square plus 600 square, and then the final answer for this calculation will be equal to 781.02 Newton. Now here we only calculated the magnitude of the force. We need to get the direction, and this is why I came here and I said opposite side, adjacent side, because using that one we can use now the tan theta, which is equal to opposite side divided by adjacent side. And if we do that, we have the tan theta is equal to opposite side is 600 divided by 500, and when you calculate this one, you get that tan theta is equal to 1,2, but this is no theta, this is tan theta, so theta is equal to 10 of the minus 1 of 1,2, and when you do that, guys, you will get that the answer is 50,19. So theta is equal to 50,19 degree, and this is the final answer. So in this question we have the magnitude of the vector at this point, that is the magnitude of the vector, and here we have the direction, which is that angle, a specific angle there. Guys, this is question 2. I don't think it's that bad. Let's go to question 3, and question 3 is a little bit more tricky, but I did the question very much the same as this one, and you can go and watch it. I'll leave the link for you to do that. Now, this question said, two inextensible ropes with negligible masses exert forces on an object with mass 10 kilograms that hang at rest as shown in the sketch below. This is at rest. That is an important detail here. The object is at rest, and therefore it means it is at equilibrium. It is at equilibrium. The first one, write down the magnitude of the net force acting on an object. This is not other thing than Newton's first law. F net is equal to 0, guys. If the object is at rest or is moving with constant velocity, then the net force is equal to 0. Okay, so that is the first answer. It's very easy. Draw a vector diagram not according to scale to motivate your answer in question 3.1. So you have to draw a vector diagram in which you can have at the end a closed triangle. So we are going to do here on the right a free body diagram, which is not the same as the vector diagram they want in this question. The free body diagram, forces acting, there is tension 2 in this direction. You have tension 1 in the other direction. Let's fix that tension 1. Try to do it a little bit better. This is tension 1, and you have weight on that object down. And this is the free body diagram, but they don't want that. They want a force diagram to show that the net force is equal to 0. So all you have to do is to add the vectors head to tail, starting from here, tail to head. So let's draw first, for instance, T2. Let's start with T2. You can start with any one. This one here is T2. Right on the head of this one, you're going to add the tail of the other vector, and you will have that this one here is T1. But guys, where is the weight? The weight must be from here, from this head all the way down, and it must be a closed diagram. Note, I did a video with an experiment to show this, how this equilibrium process of vectors at equilibrium is shown. I'll leave the link as well so you can see the diagram. Now they're asking you here to clearly show some angles. Now this 70 that you can see here is the angle between, if this one is the gravitational force, as you can see there, this 70 then is between T1 and the weight, which is this angle here. Let's use another color. So this one here, guys, is 70 degree, and the same happen on this side. If we draw here real fast for you to understand, I'm going to draw a perpendicular right on the box and this way. This one is 30. This one is 30 because it is alternated between parallel. Therefore, this one must be 60 degree, and this one could be the angle between the gravitational force and T2. In other words, if you go to the drawing, this angle will be this angle here. This one is 60 degree. They ask only for two angles. So with that one, we are done with question 3.2. I hope you understand. I'm going to clean all this one because we are going to use this drawing for the further coming question now, 3.3. Calculate the magnitude of T2. Now to do this one, we are going to go and have a clear free body diagram so you understand what is going on there. And this is the free body diagram. Now, before we carry on, we are going to first of all find out or draw the component of each of those forces. This T2 is going to be projected all the way down to the X, and you will have here T2 in X. Here, you project it to the Y-axis, and you will have here T2 in Y-axis. Now, we go to T1. Now in T1, you project to the S, same story. You have here in the X, you will have T1 in X, and if you project to the Y, you will have here Ty. All right. Now the angles, some angles are given, so let's add the angles here. So we need this angle here on this side is going to be 30 degrees. It is given to us, and we spoke about the angle just now, and these are the angle. At this point is going to be equal to 70 degrees. All right, so that one is 70 degrees. Let's do this and move it here. It is 70 degrees, so you can see the 70 properly. That one is 70 degrees. And now the bottom is weight. Weight does not have any component because it's right on the Y axis. Now, because the system is at equilibrium, I want you to see something. Because the system is at equilibrium, in x-axis f net is equal to 0 as well as in fy. F net is equal to 0. Now, let's go to the x-axis. Remember, if it's equal to 0, it means that t1 in x must be equal to t2 in x. Okay, we go in here and we have t1 in x must be equal to t2 in x. Remember, this is not t1, this is not t2. This is t1 in x and t2 in x. Now, let's go to t1 in x here. According to the angles we have, this one is the adjacent side of that angle I have there. So t2 in x, which is this is t2, is going to be equal to t2 because its adjacent side is cos 30 degrees. That is t2. And if we go to the other side here, to t1, this side will be the opposite because it becomes this one here. This one is the t1 in x. So, because it is the opposite, t1 in x is equal to t1 sin 70 degrees. The other option is to calculate, guys, the angle and then substitute it, but it's not in it. So we are going now to substitute each of these equations, each of them, into the x1 I just wrote there. So saying that t1 in x is t1 multiplied by sin 70 degrees. This one is coming from here, if anybody doesn't know where it's coming from, and is equal to t2 in x, which is coming from here, this side there. So t2 is t2 multiplied by cosine of 30 degrees. Now, here we have two unknown. We have to stop there because we don't know few things there. We don't have t2, we don't have t1. So we are going to stop there and we are going to look for this one in the y-axis, and as I did right in there. So we stop here because we don't have some data. Now, in the y-axis, what forces do we have in the y-axis? Well, in the y-axis, we have right on top, pointing up, we have t2 in y and t1 in y. And pointing down, we have the weight. So saying that, we can say that t2 in y plus t1 in y must be equal to weight. Everything top must be equal to everything down. And now from here, we need to substitute t2 in y and t1 in y, guys. So if we go here and we say that t2 in y on this side here, I'm doing it very slow because it could be confusing. It's the opposite angle, is this one I'm drawing here. So t2 in y is equal to t2 sine 30 degrees. This one is t2 in y, as you can see there. And t1 in y here is the adjacent side to the 70. So t1 in y is equal to t1 cos 70 degrees. And all we're going to do is to substitute those two in that equation there on the right. So we're going to substitute on this side a little bit down because of the space. T2 in y is going to be T2 sin 30 degrees plus T1 in y is T1 cos 70 degrees, and that is equal to weight, which is mass multiplied by acceleration due to gravity. So now here we can come and stop there and then substitute the other equation of substitute for the T2 or T1. In this case, T1 will be better. So coming from here, coming back or going back to this point here where we are, if we rearrange that formula there, we have that T1 is going to be equal to T2 multiplied by cosine of 30 degrees divided by sin 70 degrees. And here we can substitute now in this equation there. I'm doing it quite slow so you can understand why I'm actually doing. So what do we have here? T1, T2, we're going to write the T2 still, T2 sin 30 degree plus T1, but T1 is T2 cosine of 30 degrees divided by sin 70 degree, and all that is multiplied by cosine of 70 degrees, and is equal to 10 multiplied by 9,8. This is the substitution. Now when you calculate this one, when you use your calculator, you'll get that the final answer is 120,21 Newton. Guys, this is the answer. This question was a little bit more tricky, little bit more work, but not impossible to do. Please, you can rewind the video and watch this one step by step. How did I solve 3.3? There are other options that may be easier, but this is what I like to do. So this one is question 3.3. Let's go to question 4, and it's going to be the last question of this video. Then we're going to carry on with questions 5 and the rest of the question paper. The question 4 said a force of 100 Newton is applied to the crate of 8 kilograms. The crate moves up a rough incline that makes an angle of 27 degrees with the horizontal as shown in the diagram below. The crate is moving at constant velocity. Friction cannot be ignored. So constant velocity, once more we are going to be working with Newton's first law. Okay, now draw a level free body diagram to indicate all the forces acting on the crate. 4.1, we're going to do it here. What forces are acting on the crate? First, parallel to the surface is going to be the applied force. This is here the applied force. What other force is acting? Straight down is always going to be weight. This is weight down. Normal is perpendicular to the surface, so it must be in this direction. Make sure it is perpendicular to the surface. Let's fix this head of the arrow. This is normal, and there is friction to the back. The friction is parallel to the surface, but in the opposite direction of motion. Okay, so this is the question. Now these 4 marks, make sure you have 4 forces because you'll get 1 mark per force. Calculate the perpendicular component of the gravitational force. Now for that one, we're going to have a free body diagram, but full free body diagram. And we're going to do it on this side. So for that one, we are going to be adding the axes. So those are the axes. And now the components of the way you projected perpendicular to the y-axis, this one is the perpendicular component they want you to get. This one is weight in the y-axis, guys, and the angle is important to know that this angle here of inclination, this 27 degrees there, is going to be this angle here. This one is 27 degree in this case. Now on the x-axis, then this weight is going to also be projected in the x-axis, and I have the weight in x. Now from here, from the drawing, and according to the angle you have, weight in x, which we are going to use it later, is going to be equal to weight, that one will be the opposite side, sin 27 degree. And the weight in the y-axis, which is the question here, is the adjacent side to that angle and is equal to weight multiplied by cosine theta. That is the question, guys. We're going to answer that question real fast here. Weight in the y-axis, they use the term perpendicular, is the same. So here in this case is weight multiplied by cosine 27 degrees. If we carry on, weight is mass multiplied by acceleration due to gravity, cosine of 27 degrees, and this is equal, when you substitute, 8 multiplied by 9,8 multiplied by cosine of 27 degrees, and the answer is going to be 69,85 Newton. That is the correct answer for that question. Now, question 4.3, define normal force. The definition of normal force is a force of a surface on an object perpendicular to the surface. In actual fact, it's a component of the force that the surface exerts on the object, and it will be the perpendicular component. Let's go to question 4.1.1, where you do have to calculate the normal force. If we're going back to our free body diagram, not the one from Mark, but this one we draw here to work, you can see the normal force is in the y-axis, and the two forces in the y-axis are the normal as well as the weight in the y-axis. So in other words here, if you use Newton's first law for question 4.4.1, Newton first law in y, what we have here, that F net is equal to 0. Forces there is normal minus the weight in the y-axis is equal to 0, and then you know that normal is equal to weight in the y-axis, which was calculated and is 69.85 Newton. That is the answer. Now they say calculate the normal force. Normal force is a vector quantity, so it should be perpendicular to the surface, because there should be direction. It is perpendicular to the surface. Okay, so this is question 4.4.1. Now 4.4.2, calculate the coefficient of kinetic friction. Now for this one, we're going to go first of all to the formulas. Here is the formula you are going to use. This is kinetic frictional force, which is equal to kinetic coefficient of friction multiplied by normal. So let's answer that one real fast. Frictional force is equal to kinetic coefficient of friction multiplied by normal. Normal force was calculated in this question there, but frictional force we don't have it. Okay, to calculate the frictional force, we have to come here to the x-axis. And what forces do we have in the x-axis? Remember, net force in y-axis, F net is equal to 0, because we're working in the y-axis, in the x-axis, not y, x-axis, sorry, x-axis, and the object is moving at constant velocity at v constant. They tell you that. So here we have in that the applied force minus the frictional force minus the weight in the x-axis is equal to 0. We're looking for friction, guys. So if you rearrange this one, you have that frictional force is going to be equal to the applied force minus weight in x-axis. So now applied force is given, but the weight in x is not given. However, we have the formula here in our free body diagram. You can see it right there in this side. So it will be equal to, let's calculate first here, weight in x is equal to weight multiplied by a cosine of, sine theta, because it's the opposite side, sine theta, which is 27 degrees. So when you calculate this one, you have mass acceleration due to gravity multiplied by the sine of 27 degrees, and then you substitute everything here. And guys, this one is what we substitute to calculate the frictional force right in there. So frictional force is equal to applied force, which is 100 minus the 35.59, and that gives us that is going to be equal to 64.41, and we are almost done. Now we have to go all the way back there to calculate the kinetic coefficient of friction, which we are going to do on this side here down. And the answer is going to be 0.92. This is the final answer of this question, and this is the final question of this video. Next time we're going to be doing question 5, you can see it here, and we're going to do question 6 and question 7, and be the end of this video about the test of grade 11. It's a very important test because you are going to have similar questions in June and at the end of the year, guys. But without carry on, I hope you understand, I hope it helped. Subscribe for the channel if it did help, and I'll see you next time, Mr. G.